the failure mechanisms, materials you can use, and also how to pick materials based on stiffness and strength considerations when you want to minimize the weight of the system. Now, uh, next, what we will be talking about are the failure models. Okay, so in particular, we will be paying attention to the plastic yielding of material, meaning we do not want any permanent shape change occurring in the machine elements when they are loaded. We do not want the materials to deform. So we will be looking at the criteria for that, and we will also be looking at the criteria for the fatigue failure. So shape change and fatigue fracture are two things we are going to look at in detail, and we will also briefly look at the criteria for brittle fracture or fracture of the materials. Now, uh, when you take any real life component, okay, so if you take for example, let us say the uh, let us say bearings, okay. So what do you have? So if I draw the cross section of the bearing elements, okay, so what do you have? You have, okay, so this is the rotation axis, and then you have the inner raceway. Okay, so this is the inner raceway, and then you have your rolling elements. So let us say this is the rolling element, and then you have your outer raceway. Okay, so the outer raceway will uh, it will look something like this. Okay, it will look something like this. No, I made a mistake, sorry, just one second. So the outer raceway will look something like this. Okay, now in this particular case, the bearing, this one is a deep groove ball bearing, and the load that it can take is going to be radial load. Okay, so let's say FR. Now in this particular
So,
problem, yeah,
so can you zoom it? It's very, it's not visible properly.
are you looking on a mobile?
No, sir, laptop, but the screen is
uh,
vertical
okay,
actually.
just one second, let me see.
Sir, if you could just rotate the iPad.
Okay. Okay. All right. So now if I, right, the bearing is subjected to radial load. Okay. Now I do not want either the raceway. So this over here is my inner raceway. This is my outer raceway. And this is my roller. Okay, I do not want any of them to undergo permanent shape change when I am subjecting the bearing to the radial load. Now what would be the kind of stress which the material would be encountering on the raceway, on the raceways and the roller? When I say kind of stress, now until now in many courses including mechanics, solid mechanics, dynamics, in lot of courses you must have been exposed to the concept of stress. When you are exposed to the concept of stress, you would have been exposed to the parts or specimen subjected to tension or compression, bending or torsion. These are the kind of loadings which the material would have been subjected to in uh, in the problems that you have been exposed to. Okay, but then these are simpler settings, okay, of loadings. But when it comes to this particular problem, what do you think is the nature of the stress which the material is being subjected to in this problem? What do you think? Do you think it is a situation of simple compression of the material, or some simple torsional or shear stresses? What do you think would be the nature of stress within the rollers and the raceways?
Sir, it seems to be like a compressive stress situation.
It is compressive, but do you think it is going to be a uniaxial compression stress?
No, sir.
No, sir, because the support is like circular in area.
So, in this particular problem, material would be subjected to a three-dimensional state of stress, correct? Now, the whatever tests that you do on the uniaxial tensile testing machine or the torsion machines, over there it is a simple state of stress, and for that simple state of stress, you know when the material is going to undergo plastic yielding, what will be its maximum stress that it can be subjected to, and so on. Okay, so let us say you have a mild steel specimen. In uniaxial tension, it can withstand a stress of 230 megapascals, after which it will undergo permanent shape change. You have this piece of information. But then, in reality, the machine elements will be subjected to a complex three-dimensional state of stress. So one big question is, how do you use this information which is being obtained in experiments for some simple loadings like tension or compression, and extrapolate it to a more complex situation? That is where the failure models or the mathematical models come into picture. They help you do this extrapolation. Okay, but before we get to these failure models, we need to get a good understanding of stress. Okay, now we need to get a good understanding of stress. So what do I mean by this? See, whenever we are in design of machine means in machines, okay, what do you think would be the what do you think would be the kind of deformation with the machine elements would undergo? Do you think machine elements would be undergoing large deformations, or do you think they will be undergoing small deformations?
Small.
So whenever we are designing machines, okay, we want our parts to retain their shape. We do not want them to undergo large deformations, or in other words, we only want rigid body motion for our machine elements. So when you're talking about small deformations, what will happen is, even for metals, the deformation will be elastic in nature, meaning it will come back once the shape will be returned to its original configuration once you remove the loads. So whatever models, normally when we talk about failure models, there are three kinds of failure models. Stress based, let me write it here. So if you are looking at failure models, okay, so there are three types: stress based, strain based, and energy based. Okay, and energy based. Now what we will be focusing on uh, in design of machine elements would be stress based failure models. Okay, so So this is what we'll be focusing on in this particular course, and the stress-based models are of particular relevance when you are dealing with only elastic deformations. Once you get into the plastic regime, so let us say you are dealing with a manufacturing process and material will be subjected to deformation, and after some amount of stretching material will fail. In situations like that, you make use of these strain based models. Okay, and energy based, we use some means we have some energy based models in fracture mechanics, and also for failure of materials when subjected to large deformations. Okay, but in this course we'll be focusing on stress based failure models. So all right, stress based failure models. So there are 2 points that I need you to focus on, which will introduce complexity in the design. Okay, so what are the 2 things? So when you talk about the failure models, okay, so there are 2 concepts which you need to pay attention to. One is independence of the, so whatever failure model you propose, okay, it needs to be independent of the choice of coordinate system. Okay, or we need a observer independence. So whatever model we propose, we need it to be independent of coordinate system. Okay, we need it to be independent of coordinate system. Okay, and right, we need it to be independent of coordinate system. Second thing is we need it to be valid for any loading. Okay, we need it to be valid for any loading. So let us see. So now before we get to the failure models, you need to get a good understanding of the concept of stress itself. Okay, sorry for, I could have actually, okay, just a second. No? I'll select all of this. Okay, fine. Sorry, where did I go? Okay, I messed up. Just a second. Right. All right. Now, let us first learn a few things about stress. Okay. Now, the concept of stress and strain, first thing to realize is that these are defined either on the deformed configuration, in the deformed configuration, or the undeformed configuration. Okay, so what happens is that, so let us say material has got some initial shape, and upon application of load, this is undergoing some shape change. This is becoming a deformed shape. Okay, so normally, okay, we use some symbols. Okay, so omega naught and omega. Whatever quantity we define, like stress and strain, it is either defined on the initial shape or the final shape. Okay, now the quantity that you're all familiar with, it is defined on the deformed shape. Okay, so so as far as stress is concerned, more precisely, what you're all familiar with and we talk about is something called Cauchy stress, and this is defined in the okay. Let us look at some properties of stress. I don't want to spend too much time here, so I'll list out the properties. Any place you want more explanation, you can tell me. Okay, so the first thing to note is that the what is the nature, means what kind of a quantity is it. So you're all familiar with scalars and vectors, right? So something like mass, temperature, density, concentration, these are all scalars, meaning these quantities have got only a value associated with them at a point. Quantities like force, velocity, acceleration, these are all vectors or tensors of rank 1. They have a magnitude and a direction associated with them. Stress, particularly Cauchy stress, is a tensor of rank 2, or it is a second order tensor, and uh, like a vector has got three components, scalar has got one, and second order tensor has got nine components. It has nine components, and components of stress are denoted by sigma ij. You use two indices, I and j, each taking values 1, 2 and 3. So a vector would have, so if I take for example velocity vector, okay, then it would have one index. Okay, and basically this will be three components. And then if I take stress, it has two indices, each taking 3. So how many components? 3 into 3, or 3 to the power 2 components. If you take elastic modulus, it is actually a fourth order tensor, IJKL, each taking values 1, 2 and 3. So how many components would a modulus tensor have? How many components would a modulus tensor have?
81.
81. Okay, so this has 3 to the power of 4 components. So number of components of a particular quantity will depend on the rank of the tensor. Stress is a second order tensor. It will have two indices and 9 components. Okay. Next, the 9 components of stress can be written in matrix form in this manner. Okay, sigma 1 1 2 1 3 2 1 2 2 2 3 3 1 3 2 So stress has got 9 components and they can be written in index form in this particular manner. Okay. After this, now in general, Cauchy stress has got 9 components, but you can prove that, okay, you can prove that in the absence of point couples acting on the material. What is a couple? Couple is if you have a two force system. Okay, so if you have a two force system like this, where the two forces are equal and opposite but are acting across a certain distance, then the couple is simply F multiplied by L. Now, in general, so for a point couple, what happens for a point couple? For a point couple, this capital L tends to 0. So if forces are finite, then moment will tend, or couple will tend to 0. But if the couple has to be finite, even for L tending to 0, capital F must tend to infinity. So in the absence of such sort of a scenario, you can prove that for any material, any problem, whether it is static or dynamic, doesn't matter the magnitude of acceleration, you can show that sigma ij will be equal to sigma ji. How many moment balance equations do you have?
3.
In a body, I can pick any arbitrary volume of the material. How many moment balance equations will I have? How many
So 3.
scalar moment balance equations will I have?
3.
You will have 3 scalar moment balance equations, and those 3 equations will give you 3 constraints. Okay, what are the 3 constraints? Sigma 1 2 must be equal to sigma 2 1, sigma 3 1 must be equal to sigma 1 3, sigma 2 3 must be equal to sigma 3 2. So the symmetry of the Cauchy stress comes from the moment balance statement, and as long as you ensure, or as long as you assume that Cauchy stress is symmetric, moment balance within the material will be trivially satisfied. It is the moment balance which is responsible for this symmetry of the Cauchy stress. Okay. Okay. Next. Now, if you take a if you take components of a tensor, whether it is a first order tensor, second order tensor, will the components be independent of coordinate system or will they depend on coordinate system? Let us take a simpler situation. Okay, so let us say these are the 3 axes, x1, x2, x3. Let us say there is some vector v. Okay, now if I am writing down the components of this particular velocity vector, so x1 x2 x3 are one coordinate system, x1 dash, okay, x2 dash and x3 dash are another coordinate system. This velocity vector, its components, I can write it as v1 v2 v3. I can also write it as v1 dash, v2 dash, v3 dash, depending on which coordinate system I pick. So the components of this particular velocity vector, are they dependent on coordinate system or are they independent of coordinate system? Will the components of a vector depend or independent, or they won't depend on coordinate system?
Depend.
Is v1 v2
Depend.
v3 equal to v1 dash v2 dash v3 dash?
No,
No,
sir.
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 They will
It
They
is
depend.
will
not.
depend.
So components of a vector, so this is not equal to v1 dash v2 dash v3 dash. So components of a tensor will depend on the coordinate system, but will they be related or will they be totally unrelated?
So they will be related.
They will be
Related.
related because they are both referring to the same velocity vector. Is the vector depending on the coordinate system?
Yes, sir.
No, sir.
No, no,
No,
no, sir, no, sir.
velocity vector is independent of the coordinate system. It is what it is. Okay. So if a water is going through a pipe, okay, and let us say that the direction of the velocity, means the velocity will be along the length of the pipe. Okay. Now, so means the velocity vector itself is independent of the coordinate system, but its components will depend on the choice of the coordinate system. This is an important distinction that you have to make. Now, if the components depend on coordinate system, there must be some relation which is relating the two sets of components. So for that, you make use of something called transformation relations. Okay, so if you have two coordinate systems, if you have two coordinate systems, let us say x1, x2, x3, and x1 dash, x2 dash, x3 dash. So if you have two sets of coordinate systems, okay, then what you can do is and let us say e dash I are unit vectors in dashed coordinate system and ej are unit vectors in the undashed coordinate system. Then what you can do is you can relate the components of stress in the two coordinate systems through such sort of a transformation relation. Okay, so what you get is in matrix form, you get sigma dash matrix is equal to q sigma q transpose, where q is called is a rotation matrix. It is a rotation matrix, and components of q are defined through this particular relation. So qij will be equal to e dash I dotted with ej. So you can use this particular vector product in order to get the components of q. And q has got some properties. It's a rotation matrix. So what properties will it have? So q transpose will be equal to q transpose q will be equal to identity. It's a rotation matrix, so it will have the properties of q transpose equal to q transpose q equal to identity, and it will also have the property the determinant of q will be equal to plus 1. Okay, so these are the properties that the rotation matrix will have. Now the thing is this, that see, the components depend on coordinate system. Okay, so if I want to come up with some sort of a let's say a failure criteria, more precisely, let's say I want to come up with the condition for plastic yielding. Okay, so can I simply say that when sigma 11 exceeds the yield strength of the material, then you will have plastic yielding in the material? What is wrong with this statement? In uniaxial tension, okay, when material was getting loaded along x1 direction, the condition for plastic yielding was when sigma 11 exceeds yield strength of material, I will have plastic yielding. But then I cannot use this as a generalized yielding criteria. What is the problem with this statement?
Sir,
Sir,
with multi-axial tension or compression, this won't work because the assumption was
Okay, so that is one problem. It is not generic in nature. It is specifically for that uniaxial loading case. What else is the problem?
Sir, for some coordinate system, it can be well within the limit, but if we change that, then it may increase.
So for the same loading, if I choose a different coordinate system, then I will get sigma 11. So let us say for uniaxial loading, when x1 is aligned with the loading direction, then sigma 11 may be equal to 230 megapascals. But let us say when x2 is aligned with the loading direction, then sigma 11 will actually be 0. Okay, so there are two problems with that particular statement. One is it is not generic, it is not valid for all loadings. Second is it is depending on the choice of coordinate system. Whether or not yielding happens is depending on coordinate system, so it is wrong on both fronts. Okay, so we cannot be directly using components of stress in failure criteria. What we will have to do is we will have to work with something called invariants of the tensor, or there are some measures of stress, they are called measures of stress, that are independent of coordinate system. Okay, so if you take a vector, components of a vector depend on coordinate system. Which measure of a vector will be independent of coordinate system? So you know, earlier I had told you that, so if you take v, v is not equal to v dash, means components of vector are different. Okay, but what aspect of v will be equal to v dash?
The magnitude.
Magnitude. So if I take V transpose V, this will be equal to V dash transpose V dash. So the components are not the same, but the magnitude of the vector is the same. Okay. So this is called measure. This over here, this is called a measure of the tensor. My writing is bad here. So this is called a measure of the tensor. So there are some measures, and the measures which are independent of coordinate system are called invariants. Invariants. So before you want to come up with any sort of a physical criteria, okay, the criteria must always be in terms of invariants of the tensor quantities, and they should not be in terms of some generic components of the tensor. So now, what are the invariants of stress? How many independent invariants do we have? So let us look at that. So in order to get invariants of the stress, we need to know some matrix properties. Okay, so if you have three matrices A, B, and C, then I don't know how many of you are aware of this particular feature. The trace of A times B times C will be equal to trace of C A B equal to trace of B C A. How many of you are aware of this particular property of matrices? Raise your hand if you are familiar with this. Okay, so some of you are aware, many of you are not aware. Okay, so uh, this is one property, and another one which all of you must be aware is determinant of product of matrices will be equal to means determinant of A times B times C will be equal to determinant of A times determinant of B times determinant of C. So let us use these properties. So if we take trace, if we apply the trace operator, so trace of sigma dash, what will it be? It will be trace of Q times sigma times Q transpose. Now I can use the permutation rule, bring the Q transpose to the front, and this will be equal to trace of Q transpose Q sigma, but Q transpose Q is identity. So what have we shown? We have shown trace of sigma dash equal to trace of sigma. So trace is one of the invariants of stress. Okay, so please remember, trace is an invariant measure of any second order tensor, not just stress. Here we have shown it first, means I have been giving stress as an example of second order tensor, but trace of a second order tensor is an invariant measure. Now similarly, if I take determinant, so you will see that determinant of sigma dash equals to determinant of Q times determinant of sigma into determinant of Q transpose. But what is determinant of Q and determinant of Q transpose?
One.
1. So what will happen? Determinant of sigma dash will be equal to determinant of sigma. So determinant of sigma is also a stress invariant. So we already got two stress invariants. Trace is an invariant, determinant is also an invariant. Now let us look at trace of sigma dash square. Okay, so what will you get? Sigma dash square means trace of Q sigma Q transpose Q sigma Q transpose. So Q transpose Q is identity. So you end up with trace of Q times sigma square Q transpose. You can again apply the permutation rule, and you will get trace of sigma dash square is equal to trace of sigma square. So trace of sigma square is also a stress invariant. Okay. Now a second order tensor will have three independent invariants, and we found all three independent invariants. Okay. Now all three invariants. Okay. Next, let us look at the concept of traction. Okay, so what is traction? So if I have a body and I'm subjecting it to some external forces, if I consider a point P within the material, I know that material is under a state of internal stress. Okay, meaning there are some internal forces acting on the body. Now, if I consider a plane with a normal, so this is the plane passing through the point, and this is a normal to the plane. Okay, so normal, I'm representing it with n. So now I'm interested in knowing, so if I sort of separate them out and draw the free body diagram, what is the force per unit area acting on this plane at this point? That is called traction. Okay, that is called traction. So traction is denoted by, it is denoted by T. Okay, in general, this force per unit area that need not act along the normal, it can act along any direction. Okay, so it will have a normal component and a shear component or tangential to the plane. Now what can be shown is traction acting on a plane is related to stress at that point using this particular relation. So sigma means in matrix form, traction vector is equal to sigma transpose n. Okay, this is a very, very useful relation. So for any plane passing through the point, you can estimate the force per unit area on that plane using this particular relation. Okay. Now, so there is a special means when the traction vector is along the normal to that particular plane, then what will happen? Then you have a situation where sigma transpose n is equal to lambda n. So when traction vector is along the normal, okay. So when traction vector is along the normal, what will happen to the shear component?
That will be 0.
0.
So shear component will be 0. Such sort of planes on which the traction vector is along the normal, they are called principal planes. Okay. So these are very, they play a very important role. So planes passing through a point on which you do not have any shear component of stress, these are called principal planes. And the normal traction acting on such planes, they are called principal stresses. Okay, so how do you get principal stresses? You get principal stresses by solving this equation. Okay, now remember sigma equal to sigma transpose, so sigma transpose n equal to lambda n can also be written as sigma n equal to lambda n. Now how do you get the principal stresses? You get the principal stresses by solving this equation, determinant of sigma minus lambda equal to 0. The equation that you get, what do you call this equation? You call it as the characteristic equation. Okay, so this is the characteristic equation for principal stresses. What is the order of this equation?
3.
It is a cubic equation in lambda. So how many principal stresses will you have?
3.
You will have 3 principal stresses. Now the characteristic equation can be written, finally you can write the characteristic equation like this. Now what can you say about the coefficients of the characteristic equation? What can you say about the coefficients of the characteristic equation? What is special about them?
Invariants.
So the coefficients of the characteristic equations are invariants, okay? Which means that you can determine this characteristic equation in any coordinate system and it will all be the same. So if the coefficients are invariants, what can you say about principal stresses? The
They are
principal
also
stresses
same.
are also invariants,
Variant.
okay? So whenever you're coming up with models, you can come up with them either in terms of the principal stresses or you can come up with them in terms of trace of sigma, determinant of sigma and trace of sigma square. Now, even though both of them are invariants, okay, which would be easier to work with?
Principal stresses.
No, principal stresses relations are simpler. but they will be difficult to work with because you have to solve the characteristic equation in order to get the principal stresses, whereas the other invariants can be obtained directly in terms of the stress matrix. Okay. Now, the one important point is principal stresses are unique. There are three principal stresses, but the principal planes need not be unique. There are minimum of three mutually perpendicular principal planes. Okay, there is at least one set of mutually perpendicular principal planes, but you can have many of them. So for example, if you have pure hydrostatic stress, how many principal planes will be there? For a pure hydrostatic state of stress, on what all planes will the traction be normal to the plane?
So all possible
All
sets.
planes or any plane that you take will be a principal plane for a pure hydrostatic state of stress. So like you can have infinite principal planes. The case in point is hydrostatic state of stress, pure hydrostatic state of stress, but principal stresses are unique. So for hydrostatic stress they are identical but they are unique, but principal planes need not be unique. Okay. Now, another point is, so the maximum shear stress on any plane passing through a point can be written in terms of principal stress as sigma 1 minus sigma 3 by 2. And von Mises state of stress, von Mises stress, which you must have encountered in many places, okay, can be written in terms of the stress invariants like this. So you can write it as, so sigma von Mises can be written like this. Okay, square root of half into 3 times trace of sigma square minus trace of sigma whole square. So is von Mises stress an invariant or not an invariant?
It is invariant.
So von Mises stress is also a stress invariant. Okay. In fact, von Mises stress is the most widely used stress invariant. So most popular stress invariants are von Mises stress, hydrostatic stress, and the principal stresses. These are the most popularly used stress invariants. Okay. All right. So I'm going to stop here. I'll share that questions and you can start answering. Try to finish it off before the in 10 minutes. Okay. Do not take much time.
Sir, what is the difference between hydrostatic and principal stress like element invariants?
Just give me a minute. I'll. All right, so I have pasted the form in the chat. So please start answering the questions. Yeah, if you have any questions, you can ask now. So you were asking?
Sir, like principal stress matrix and hydrostatic stress matrix, like the electron tensor, sir, are they different? Hydrostatic will be the
Yeah, yeah.
average.
So I'll show you. So hydrostatic stress. So sorry. So hydrostatic pressure is defined as minus trace of sigma by 3. Okay, this is true in any coordinate system. So this will be minus of 1 1 2 2 3 3 by 3. In terms of principal stresses also, this is minus of sigma 1 plus 2 plus 3 by 3.
Thank you.
Yeah.